There are truths about the universe that almost no one ever tells you, not because they're hidden behind secrecy, not because of some shadowy conspiracy, but because they're so bizarre, so unintuitive, and so deeply unsettling that they rarely make it into popular science books, documentaries, or even most university physics courses. I've spent my entire professional life working on the deepest problems in fundamental physics. Along the way, I've encountered ideas that most people never hear about. Ideas that would completely transform how you see reality if you truly absorbed them. Ideas that even many physicists prefer not to stare at too long because they clash so violently with our everyday intuition. So let me tell you what you're never told about the universe. The uncomfortable discoveries physics has made, but that usually stay confined to advanced research papers and specialist seminars. The first thing you're never told is that the universe might be finite in a way that barely makes sense to the human mind. We often talk about the observable universe being finite, limited by a cosmological horizon beyond which we can't see. That idea feels reasonable. But the universe itself might be finite in a much deeper sense, finite in total information content. According to the holographic principle, the maximum amount of information contained in any region of space is proportional not to its volume, but to the area of its boundary. If our universe has a cosmological horizon, then the total amount of information it can contain is finite, determined by the area of that horizon. This implies that there are only finitely many possible quantum states the universe can occupy, only finitely many possible histories, only finitely many possible configurations of everything that exists. The number is unimaginably enormous, far beyond comprehension, but it is still finite. What does that mean? It means that, in a very real sense, the universe behaves like a finite computer running a finite program. There are only so many bits of information in total, only so many things that can ever happen. This idea almost never appears in popular science because it's profoundly strange. We like to imagine the universe as infinite in possibility, limitless in what can occur. But fundamental physics suggests something very different, a universe that is bounded, constrained, and ultimately finite. You're never told that the universe has a maximum information capacity and that this maximum is not infinite. The second thing you're never told is that most of the universe is completely inaccessible to us and always will be. Not just inaccessible with current technology, but inaccessible in principle, forever. The cosmological horizon isn't merely a temporary limit on what we can see right now. It's a fundamental boundary of causality. Regions beyond it are causally disconnected from us. Light from those regions will never reach us. We can never travel there, never communicate with them, never receive any information from them. And because dark energy is driving the accelerated expansion of the universe, this horizon isn't growing to include more regions. It's roughly fixed, and may even shrink in relative terms. Galaxies are steadily crossing this horizon and vanishing from our observable universe forever. In 1 trillion years, almost every galaxy we can currently see will be gone from view. Future astronomers will observe a universe that looks nearly empty, containing only our local group of galaxies and nothing beyond. All observational evidence of the Big Bang, of cosmic expansion, of the vast, large-scale universe will have disappeared. You're never told that we live in a special moment in cosmic history, possibly the only era when the large-scale structure of the universe is observable, and that this window is temporary. Future civilizations will be cosmologically blind. The third thing you're never told is that quantum mechanics tells us that nothing is truly real until it's measured, and that no one actually knows what measurement means. Before measurement, particles don't have definite positions or velocities. They exist in superpositions, effectively occupying multiple states at once. But what exactly counts as a measurement? Does it require a conscious observer? Can a machine perform a measurement? Can an atom measure another atom? Where precisely does the quantum world end and the classical world begin? No one knows. This is known as the measurement problem, and it has remained unsolved for nearly 100 years. Every interpretation of quantum mechanics offers a different answer, and we have no experimental way to determine which interpretation is correct. Some interpretations suggest consciousness causes the collapse of the wave function. Others claim there is no collapse at all, only branching into multiple worlds. Still others propose an objective collapse mechanism we haven't yet discovered. Some argue the question itself is meaningless. The reality is that we do not understand measurement. We don't understand how a fuzzy quantum world gives rise to the definite classical world we experience. We don't understand the role of the observer. This isn't a minor technical detail. It's a fundamental hole in our understanding of reality. You're never told that physics does not know how possibilities become actual outcomes, how the world becomes definite. The fourth thing you're never told is that the laws of physics might not be universal. We usually assume that the laws we discover apply everywhere and at all times. But that's an assumption, not an established fact. In scenarios involving eternal inflation and the multiverse, different bubble universes can possess different effective laws of physics, different constants, different particles, and different forces. What we call the laws of physics may simply be the local rules governing our particular cosmic region. Even within our own universe, the effective laws change depending on the energy scale. At low energies, we have the standard model. At higher energies, new physics emerges. At the Planck scale, space-time itself may cease to exist in any familiar form, requiring entirely new laws. Physics appears to be scale-dependent, regime-dependent, and possibly location-dependent. There may be no single set of universal laws, only effective descriptions that work in specific contexts. You're never told that the laws of physics might be emergent, local, and provisional, rather than fundamental and universal. The fifth thing you're never told is that time may not be fundamental, and might not even exist at the deepest level of reality. In quantum cosmology, the Wheeler-DeWitt equation contains no time variable at all. Time emerges only when we divide the universe into subsystems and use one of them as a clock. Different choices of clocks lead to different notions of time. Time is not unique, not absolute, and not fundamental. It's an emergent bookkeeping tool. Even the arrow of time, the distinction between past and future, is not fundamental. It arises from thermodynamics, from increasing entropy, from coarse graining and limited information. At the microscopic level, the laws of physics are largely time-symmetric. The flow of time, the sensation that time passes, the distinction between past and future, these may all be emergent phenomena, artifacts of how we, as thermodynamic systems, experience the universe. You're never told that time might not be real in a fundamental sense, that it could be observer-dependent and possibly illusory. The sixth thing you're never told is that empty space is not empty at all. The vacuum seethes with quantum fluctuations, virtual particles constantly appearing and disappearing, fields fluctuating everywhere. These fluctuations are real. They shift atomic energy levels. They produce the Casimir effect. They cause black holes to emit radiation. The vacuum has structure, energy, and measurable physical consequences. But here's the truly shocking part. When we calculate the energy density of empty space using quantum field theory, we get a value that is wrong by a factor of 10 to the 120, not 120 orders of magnitude, 10 to the power of 120 orders of magnitude. This discrepancy between theory and observation is known as the cosmological constant problem, and it's the worst prediction in the history of physics. Why is the vacuum energy so small? Why isn't it zero? Why does it have exactly the tiny value we observe? No one knows. It's a complete mystery. You're never told that our best theory produces the most catastrophically wrong prediction ever, and that we have no idea why. The seventh thing you're never told is that most of the universe is made of stuff we don't understand. About 27% of the universe's energy content is dark matter. We know it exists because of its gravitational effects, but we have no idea what it's made of. It's not composed of any known particle. About 68% of the universe is dark energy, which drives cosmic acceleration. We know what it does, but not what it is. It might be the cosmological constant, a new field, or something entirely different. Add it up, and roughly 95% of the universe consists of unknown components. We understand only the remaining 5%, the ordinary matter made of atoms. You're never told that physics only understands a tiny fraction of what the universe is actually made of. The eighth thing you're never told is that the universe might not have had a beginning. The Big Bang is often described as the origin of space and time, But that's not quite accurate. The Big Bang marks the beginning of the hot, dense expansion phase we can describe with our current theories. It's the point beyond which our equations stop working. But it may not represent an absolute beginning. In some models, such as eternal inflation, the universe has always existed in some form, constantly spawning new regions like ours. Our Big Bang would then be a local event in a much larger, timeless structure. In some quantum cosmology models, time itself is emergent, making the question of a beginning meaningless. Asking what happened before the Big Bang may be like asking what lies north of the North Pole. You're never told that the universe might be eternal, or that the concept of a temporal origin might not apply at all. The ninth thing you're never told is that black holes might not have interiors. Classically, we imagine black holes as objects with an event horizon surrounding an interior region that leads to a singularity. But quantum mechanics and the holographic principle suggest a radically different picture. All the information associated with a black hole may be encoded on its two-dimensional event horizon. The interior could be an emergent holographic description rather than a physically independent region of space. From an external perspective, infalling matter never actually crosses the horizon. It appears to freeze there, with its information smeared across the surface. The interior description may be a complementary viewpoint, not a literal place that exists independently. Black holes might be fundamentally two-dimensional objects with no true interior at all. You're never told that black hole interiors may be holographic illusions rather than real regions of space. The 10th thing you're never told is that the universe is probably not computable. A computable universe would be one whose future evolution could, in principle, be calculated exactly given initial conditions. But quantum mechanics contains true randomness, as demonstrated by Bell's theorem and experiments. This randomness is fundamental, not the result of hidden variables. On top of that, self-reference introduces uncomputability. Gödel's incompleteness theorems show that sufficiently complex systems cannot fully describe themselves. The universe contains observers who attempt to understand the universe, creating a self-referential loop. A universe that includes such observers may not be fully computable. There may be truths about the universe that no algorithm can calculate. You're never told that reality itself may be fundamentally uncomputable. The 11th thing you're never told is that consciousness might be essential to quantum mechanics or might be completely irrelevant, and we have no way to tell which. Some interpretations propose that consciousness causes the collapse of the wave function. Others argue that consciousness plays no special role whatsoever. Experiments cannot distinguish between these views. We can observe correlations between consciousness and measurement outcomes, but we cannot determine causation. We can't step outside our own consciousness to test its role objectively. The connection between mind and matter may be fundamental, or it may be non-existent, and we may never know. You're never told that the relationship between consciousness and physics is entirely unresolved and possibly untestable. The 12th thing you're never told is that space-time itself may be discrete at the smallest scales, composed of indivisible units. Theories of quantum gravity suggest this, as does string theory. The Planck length may represent the smallest meaningful distance, but this scale is so tiny, about 1035 meters, that it may be impossible to probe experimentally. Any attempt to examine such small distances would require so much energy that it would create a black hole. There may be a fundamental limit to observation. We might never know whether space-time is discrete or continuous. You're never told that some questions about reality may be permanently beyond experimental reach. The 13th thing you're never told is that fundamental constants, like the fine structure constant, approximately 137, are deeply mysterious. This number determines the strength of electromagnetic interactions. We measure it with extraordinary precision, but we have no idea why it has this value. Richard Feynman famously called it one of the greatest mysteries in physics. It's just a number we plug into equations, and there are about 20 such unexplained parameters in the standard model. Particle masses, coupling strengths, mixing angles, all measured, none derived from deeper principles. You're never told that physics relies on dozens of fundamental numbers it cannot explain. The 14th thing you're never told is that the black hole information paradox is not fully resolved. When black holes evaporate via Hawking radiation, does the information about what fell in escape, or is it destroyed? Quantum mechanics demands that information is conserved, but Hawking's original calculations suggested it was lost. Most physicists now believe information escapes in subtle correlations, but how this happens remains debated. Multiple competing explanations exist, and no consensus has been reached. You're never told that one of the deepest paradoxes in physics is only partially understood and still controversial. The 15th thing you're never told is that the universe might be a simulation, and we have no way to rule it out. If we were inside a sufficiently advanced simulation, how could we tell? The simulation could reproduce consistent physical laws and hide any evidence of its artificial nature. Some argue that if advanced civilizations run many simulations, then statistically we're more likely to be in one than in base reality. Others dismiss this as untestable philosophy, but the key point remains: we cannot falsify the idea. You're never told that the simulation hypothesis may be forever untestable. The 16th thing you're never told is that infinity might not exist in physical reality. Physics uses infinity constantly, but these are mathematical idealizations. In reality, space and time may be finite or emergent. Whenever infinities appear in our equations, singularities, divergences, it's often a sign that the theory has broken down. Reality may be fundamentally finite, with infinity serving only as a mathematical convenience. You're never told that infinity might not be a feature of the real universe. The 17th thing you're never told is that the wave function of the universe may include all possible universes at once. In the many worlds interpretation, every quantum measurement produces branching realities. Applied to the entire universe, this yields a universal wave function containing all possible histories. Every possible version of you exists in some branch. This isn't science fiction. It's a straightforward implication of quantum mechanics without collapse. You're never told that everything that can happen may actually happen somewhere in the quantum state. The 18th thing you're never told is that observers might play a role in bringing reality into existence. In certain quantum experiments, measurements made now seem to affect how the past behaves. John Wheeler proposed a participatory universe where observers help define reality through observation. This idea is controversial, but it follows logically from quantum mechanics. Observation may not just reveal reality, it may help create it. You're never told that observers might be fundamental to the universe taking on a definite form. The 19th thing you're never told is that the anthropic principle may explain many features of the universe, and that if so, there may be no deeper explanation. We observe constants compatible with life because only such universes can host observers. If this is true, some questions have no deeper answers. You're never told that selection effects might be the final explanation for certain cosmic features. The 20th thing you're never told is that there may be fundamental limits to knowledge itself. Mathematical, computational, quantum, and cosmological constraints all point toward boundaries we cannot cross. Some truths may be unknowable in principle. Reality may contain mysteries that no amount of intelligence can unravel. You're never told that mystery itself might be fundamental. These things aren't hidden out of malice, they're uncomfortable. They disrupt the comforting story of science as a steady march toward complete understanding, but they are real implications of our best theories. Physics has been wildly successful, yet at its core it remains riddled with profound mysteries. And that's not depressing, it's what makes it extraordinary. The deepest truth you're never told is this: fundamental reality is nothing like everyday experience suggests. Space, time, objects, and causality are emergent approximations. At the deepest level, reality is abstract, mathematical, and profoundly strange. We may never make it intuitive, but through science we can still understand it. Bit by bit, mystery by mystery. Even if that understanding reveals that the universe is far stranger than anything we ever imagined.